Hi everyone, in this video I'll talk about my paper Joint Optimization of Geometric and Probabilistic Constellation Shaping for OFDM-ISAC systems, which was accepted on the IEEE Symposium on Joint Communication and Sensing in Oulu, Finland, which took place end of January 25. So let's dive right in. Integrated sensing and communications has the potential to increase the spectral efficiency significantly by using a joint waveform for communications and for sensing. However, this also introduces trade-offs. For sensing, we prefer deterministic, especially unit modulus signals. For communications, on the other hand, we need random signals to convey information, with the Gaussian distribution maximizing the mutual information. So as the optimal channel input distribution is fundamentally different, ISAC systems are subject to the so-called random deterministic trade-off. This makes the constellation, which determines the channel input distribution, a crucial factor when designing ISAC systems. So conventional communication systems use quadrature amplitude modulation. What you can see here is a constellation diagram of a 64 QRM. So now the question arises, how can we modify this constellation such that we can approximate arbitrary channel input distribution, here for example a Gaussian, which might optimize the ISAC performance. And so there are three options to do so. The first one is geometric constellation shaping, where we optimize the location of the constellation points while assuming they're equally probable. The second option is probabilistic constellation shaping, where we use the location of our conventional QAM, but optimize their probability of occurrence. So here the size of a constellation point corresponds to the probability of occurrence of this constellation points. And finally, there's joint constellation shaping, where we optimize the location and also the probability distribution of these constellation points. So this shows that we can actually use the channel input distribution, or at least the constellation, as an additional degree of freedom when we design ISAC systems. And this raises now two questions. So first, we want to understand in this talk, how does the constellation impact the ISAC, especially the sensing performance? And then in the second part of the presentation, we want to use this knowledge to optimize constellations for ISAC, which hopefully outperform our conventional modulation formats, for example, like this QAM here. So in this presentation, we consider a practical monostatic ISAC system. So we have here an ISAC transmitter whose transmit signal is used for communications and also for sensing. And in our monostatic or quasi-monostatic setup, the sensing receiver is co-located with the ISAC transmitter. So the sensing receiver knows the transmitted symbols. So further, we consider a bit interleaved coded modulation system, so a practical communication system. Here, the FEC encoder outputs bits, which are then mapped onto modulation symbols out of a modulation alphabet X. So those are our constellation points. And since our modulation symbols are random, we can consider X as a random variable. So then the OFDM modulator generates the transmit signal, which is for communications transmitted over an AWHGN channel. At the communications receiver, the signal is then transformed into the frequency domain. We have a modulation demapper, which calculates the LLRs, which are a measure for the reliability of a bit. And then finally, we calculate the bitwise mutual information as a performance metric, since the bitwise mutual information is an achievable rate in practical bit interleaved coded modulation systems. So we use the BMI to assess the impact of the constellation onto the communications performance. For sensing, we consider an arbitrary but fixed channel with J-static point targets. This allows us to write the received signal as a superposition of J attenuated and delayed versions of the transmit signal. In the frequency domain, this corresponds then to a pointwise multiplication of the transmit symbols with J complex oscillations. The received symbols are then fed together with the transmit symbols to a matched filter, which estimates the sensing channel in the frequency domain. However, since we are interested in the delay domain channel estimate, the frequency domain channel estimate is passed to an FFT before the delay domain channel estimate is passed to the cell averaging CIFAR algorithm, which determines whether a target is present at a certain delay. So now the fundamental question arises: how does the detection probability after the CIFAR algorithm depend on our used modulation X? To answer this question, we will now go through the sensing receiver architecture in the reverse order. So for the detection probability after the CIFAR, we find that it only depends on the false alarm rate, which is usually fixed in the design process, and the signal to interference and noise ratio SINR going or at the input of the CIFAR algorithm. So in order to increase the detection probability, we need to increase the SINR at the output of the IFFT. To analyze the impact of the IFFT onto the SINR, we split the frequency domain channel estimate H hat into the signal power and the noise and interference power. So the signal power H stems mainly from the target, and we can observe that it through the IFFT it experiences a processing gain, but otherwise depends only on the properties of the target, and so we cannot influence it. For the noise and interference power, on the other hand, we find that the variance in the delay domain channel estimate is equal to the variance in the frequency domain channel estimate. And so if we want to increase the SINR at the output of the IFFT, we have to decrease the variance in the frequency domain channel estimate here at the output of the matched filter. And this variance in the frequency domain is now something which we can actually calculate. And for this, we use the definition of the matched filter, and we find that the channel estimate here still depends on our modulation symbols X. And if the power of our modulation symbols X is unequal to 1, they disturb the channel estimate. And so now if we do the math, we find for the variance of the frequency domain channel estimate that it actually depends on the fourth moment of our constellation. And this is now a very nice result, because with this we are able to connect the detection probability at the output of the CIFAR to the constellation of our ISAC system. And so the fourth moment of our constellation is also often denoted as the kurtosis. And so we were now able to show the detection probability of our ISAC system depends only on the kurtosis of the constellation which we use. Now let's have a look at the two examples from the beginning. So for a unit modulus constellation, which maximizes sensing performance, we find that it has a kurtosis of 1. And so the variance in the frequency domain channel estimate just corresponds to the noise power in the sensing channel. For a complex Gaussian, maximizing the mutual information, we find that it has a kurtosis of 2, and so an additional interference term here is introduced and our variance is increased compared to the unit modulus case. So this means now that the kurtosis is basically between two extremes, one for this unit modulus constellation or for this unit modulus distributions, and 2 for a complex Gaussian. This leads now to the following optimization problem. So we want to find the constellation, so the set of constellation points and their probability distribution, which maximize the bitwise mutual information. So basically the data rate which we can achieve in a practical communication system, subject to detection probability constraint, which is expressed here in terms of kappa tilde, since the kurtosis directly relates to detection probability, as we have seen previously. So now, in order to solve this optimization problem, we use communications autoencoder. And in the following, we will now introduce or include the sensing constraint into this communications autoencoder. So autoencoders are a concept from machine learning, where encoder and decoder, so in our case transmitter and receiver, are both implemented as differentiable blocks. And this allows us to optimize the complete system in an end-to-end manner. In our case, we are able to optimize the constellations numerically. So here then in our modulation mapper, the probabilities and the constellation points are both implemented as trainable linear layers without a bias, and depending on what we want to optimize, those parameters are then considered as fixed or as trainable. So then for the training, or our distribution sampler generates a batch of 100 vectors, which are then used to generate the transmit symbols. Then we simulate the transmission over an AWGN channel before the symbols are passed through a Gaussian non-trainable Gaussian demapper. And finally, then we calculate the bitwise mutual information and backpropagate, and this is how we optimize our constellations, at least for communications only. So now to include the sensing performance in our setup, we propose now a novel loss function. And this loss function adds a penalty if this kurtosis constraint kappa tilde is violated. So then we end up with a loss function which comprises out of the communications performance and the sensing performance. For our simulations, we consider a FR2 OFDM-ISAC system with communications SNR of 10 dB. And since the kurtosis constraints should be between 1 and 2, we sweep the kurtosis constraint between 1 and 2 and optimize the constellations for each kurtosis constraint independently. So what you can see here now are our optimized constellations for a very strict sensing constraint. So here kappa tilde equals 1.0. And as expected, we actually obtain constellations which have a unit modulus. So here again, as a reminder, in this case of probabilistic constellation shaping, the size of the constellation points corresponds to their probability of occurrence. For a large kurtosis constraint, we find that our constellations resemble a Gaussian-like distribution also, as we expected. And for an intermediate kurtosis constraint, we now learn a mix between these unit modulus constellations, which we saw here, and the Gaussian-like constellations here. To assess the sensing performance, we consider a scenario with two targets. First, a distant interfering target, for example, a building with a large radar cross-section, and a target of interest, so the target which we want to detect, for example, a drone with a very small radar cross-section. And what you can see now here are our analytically derived constellation-dependent detection probabilities. And what we can observe when the kurtosis constraint kappa tilde increases, the detection probability decreases. Those markers represent now our optimized constellation formats. And here we can make two observations. First, we see that the detection probability actually does not depend on the shaping method. And now the second observation is that it actually depends only on the kurtosis of the constellation, and this then justifies or explains the first point. So the detection probability actually does not depend on the shaping method. Instead, it depends only on the kurtosis. And so it does not really matter if we have a probabilistic or a geometric constellation. As long as they have the same kurtosis, they will have the same detection probability. So very interesting result. This brings me then already to the highlight of this presentation. So here we will now compare the different shaping methods, geometric, probabilistic, and joint, in terms of their communication sensing trade-off. So for a very strict sensing constraint, so small kurtosis, we find that geometric constellation shaping outperforms probabilistic constellation shaping. And this means that geometric shaping is more suited for sensing-centric applications where strict sensing constraints are more likely. On the other hand, for a large kurtosis constraint, we find that probabilistic constellation shaping can close the shaping gap much better than geometric constellation shaping. So we can conclude that probabilistic constellation shaping is more suited for communication-centric ISAC systems. Joint constellation shaping now inherits the degrees of freedom and therefore the advantages of both shaping methods. And so with joint constellation shaping, we are now able to achieve the performance of the superior shaping method. If we now compare ourselves to legacy constellation formats like 64 QRM, we find that we are not only able to improve the communications and the sensing performance here at the same time, but so compared to those, or to only 2 operation points with those 2 conventional modulation formats, we are now able to achieve a flexible trade-off between communications and sensing with communication with constellation shaping. And I think this is a very nice advantage for ISAC systems which need to be able to deliver sensing and communications capabilities dynamically and efficiently. So let's conclude. What have we learned? So first, we derived the constellation dependent detection probability, and here we saw that the detection probability is actually independent of the shaping method and depends only on the kurtosis of the constellation. Next, we proposed a novel loss function to optimize constellations for ISAC using our autoencoder framework. Next, we compared geometric, probabilistic and joint constellation shaping, and here we observed that geometric is more suited for sensing-centric ISAC system, probabilistic shaping more for communication-centric, and joint shaping inherits the advantages of both and gives therefore the superior performance and is suited for sensing and communication-centric ISAC systems. And finally, we showed that constellation shaping is able to outperform legacy modulation formats and enables a flexible trade-off between communications and sensing. Thank you for your attention. If you have any questions, feel free to write me an email or to contact my co-authors. And yeah, thanks again for watching. Looking forward to your questions.